Um, well, there's another thing about teaching, I think, which is that it's really good to teach about things we really know. You've probably seen that. You try to write a term paper on something that you don't really know. Isn't that a little harder? So I try to apply that as well. Professor Eager, I think, intuitively does that. So before we get too much into the detail of this semester, I want to just say a few words because I see we always have a split between material science people and other departments. There's a lot of course too. I'm kind of a mechanical engineer as well, so I can relate to that. I've worked in aerospace as well, so I will not necessarily assume that you know a whole lot, but at the same time I will be brief in kind of the introduction when we want, because we're going to want to talk about structural materials in a relatively detailed way. I think that you'll realize that we make a lot of structures in a very efficient manner, and that's actually Professor Eager's module in material selection. It's a 12-hour unit that you did about 2 years ago, maybe. Essentially emphasizing if you can get by with gravel for roads, you use gravel, and then for a lot of other things you use steel, but it's on a cost basis. And then if you go to a next level, which is a little bit what we're going to do this semester, is okay, so you decided roughly what is the value here, what you're trying to build, and then there's so many options to build structural materials. You can use castings, you can use wrought product, plates, and everything that's already been processed heavily before you have it. You can make joints. It's a lot more efficient a lot of time than try to make a very complex structure all at once. You can do additive manufacturing. So we'll go over a lot, surface modification. We'll go over a lot of that, and I'll try to bring in for each topic very specific examples. Now, it all boils down to this process of using materials. So they're being processed, they do have an internal structure, they have properties, including mechanical properties. For structural material, that's what we're going to be focusing about. I will talk about environmental resistance a little bit. We're going to talk about processing of plastics and also designing for corrosion protection. But a lot of it, in terms of a structured material, it has to fit the function. And if it's a structure, then it needs to resist some loads under a certain condition of environment, temperature, and all that. So it's just to give you some idea of where we're going here in terms of when I say structural material, that's what I'm thinking. And the other thing I always think, and what I've been doing a lot in my consulting practice, is you have two sides to the equation whether you're designing something, whether you're analyzing a failure. You have what happened in terms of the loading, what was the demand on the material or the structure, and then what was the capacity, whether it was the intended capacity. So sometimes you'll talk about a minimum allowable strength. So if you do a material, it needs to be at least this good. But a lot of this comes from processing, from the way you load it, whether it's just a single load, whether it's multiple loads. So this, in the past, helped me a lot trying to analyze a situation. When we're talking about, a real problem, like Professor Eager said, you don't have, 4 pieces of information and you try to put it together. You have to look for the information. So when you go and look for the information in general, if you had a failure or if you're designing something, you want to know what is going to be the applied condition, what is going to be the demand, and then given how I'm going to build it, how strong is that material going to be? And you want a certain ratio between them, and we talk about a factor of safety then. So what I want to say as far as taking the class multiple times, I like it. I'm glad you guys like the class. I do tend to have a certain consistency for each fall and each spring. So in the fall, I focus more on the processing of the material, and I relate it to the consequences on the factor of safety, and I give a lot of example of failure analysis, but it's a little bit more about, okay, so I have this certain material, how can I best use it? type of situation. Whereas in the spring, I take a very different approach. I say more, well, okay, so we're trying to build something like a wind tower or something very, very specific. How are we going to do this? So we have to select the material, then we have to specify it. So it's not enough to say, oh, why don't you make this out of aluminum for me? I mean, it's you know, there's so many differences. And that involves the quality control and eventually the factor of safety. And I do bring in also examples of failure analysis related to that. So that's a little bit how the difference is. And I do also lecture on a very specific topic of fracture and fatigue every other spring, and it's going to be going on this spring. Now, where does that come from? I graduated from here with the PhD in 2006, so it's been 9 years now that I'm a full-time consultant. And I've had the experience to work on the World Trade Center collapse from a very different standpoint. I didn't make the news. I was part of the NIST team, essentially refining what Professor Eager had already said. You know, it took a year instead of 3 hours, to tell you the truth, to essentially identify the problem with the connections. So it ties in very well, so I may as well go ahead and talk about it a little bit more. So what Professor Eager mentioned in his article is if you have the steel column, first of all, they're embedded in concrete, okay? So it will take time for the heat to go to them, but the idea that they will just collapse on their own and buckle was not reasonable to him, just from a very brief review. And it's true. So after a very, very detailed review, and I'll show you some images. I didn't think you were going to talk about World Trade Center, but what really happened is, say you have these two beam columns, and then you have floor joists going between them. So these floor joists are steel structures that are pretty slender. There are probably some right above here. We just don't see them. And then you can have a concrete floor panel on top of it. So say this is the exact structure for now. The steel you'll see if you go to Walmart or Costco, or you just look up even in the airport. So you have these joists. So that steel got heated very quickly during the fire. And it wasn't a question of getting it to a melting point. It just had to become soft enough that it started to deform and become a little bit like a rope. And it pulled on the columns. So at least the NIST study points to this effect, having there was a very good connection between the floor joist and the column. So when you started deforming and bending, essentially the entire joist shrinks in length and pulls. It pulls on each side, just like if I'm just hanging clothes on a clothesline. So knowing this detail, it may look pretty, okay, so what? Well, if we're going to want to avoid this happening again, there are a lot of ways. We can make this connection much weaker, so it will fail and not pull on the column, or just avoid altogether having this thin steel exposed to high temperatures. So there was a lot done in terms of the fire protection code for insulating critical component of steel structures in buildings after 9/11, not just for super tall buildings, but for other structures, because they realized, oh, it's very nice to have the main structure very solid, but what if it becomes unstable for other reasons? Now, in terms of just to tie it back into the failure analysis, there was an image from an airplane taken showing just before the collapse how there was one story that the beam just pulled in. So that was kind of the visual confirmation to us that we were making sense with all our model and all our calculation. So in terms of the failure analysis, perhaps the point to remember here is a lot of times it's very nice, you've done a lot of analysis, but does it fit with what really happened? So it's always good to go back to see what you can learn. I mean, we can't go back into the building, there wasn't any sensors, but just seeing the buckling, the pulling in from the outside of the building was a confirmation that this theory was solid. All right, so that's that's for this one.
Connections failed, and that's why it collapsed. You figured out numerically
Yeah.
exactly how much capacity they had.
Well, and there's always a lot of assumption. And that's why it's always good to go back also with what the evidence showed. But once you detail your failure mechanism, when you go back to photographs, videos, you know what you're looking for. So what was triggered first? And there will be cases, I've worked on the I-35 bridge collapse in Minneapolis. That was in 2007, I believe. And we didn't have as much information. There was only a security camera that was not showing where the start of the bridge collapsed, so we just really had to work from the broken pieces as opposed to actually seeing what happened. So it can be a little bit more complicated, but I think that maybe you'll see through the different example I'll show that it's a combination of examination and analysis that I've been doing as a consultant. And that a lot of times is how you can put the pieces back together and know what happens in the details. One thing I want to bring up today, we only have a little bit more time, is a new venture that I'm leading. It's essentially a startup company. We're developing a mechanical tester, a portable mechanical tester, mostly for oil and gas pipeline. The reason is we have 300,000 miles of oil and gas pipelines in the U.S., transmission pipelines. If you include smaller pipes, it goes to about 2 million miles. So there's a lot of back and forth, and you can see in the south there's more of it, but it's all over the country. There's also a lot in Canada. Canada has about 70,000 miles, and Europe is very small, relatively speaking. The problem with these transmission pipeline is they are very reliable, but about every 6 months there's a catastrophic failure. And there are a number of reasons for that. The first one is they are aging infrastructures. Most of them were built prior to 1970. Every time that there's a gas leak, for example, and it does ignite, it's a big fire. Every time that there's a leak that's unnoticed right away, it's a big spill if it's oil. So these are kind of high consequence events, and therefore the regulators are pushing for better ways to test these materials. And here's a little bit of a reason why we believe it's going to happen. They made a lot of improvements over the past 10 years in reducing the amount of failures just because of corrosion. So the pipes are underground and they do have cathodic protection. So they have a coating and they have an electrical current that's preventing them from corroding from the outside, except every once in a while that protection is not sufficient, and then you have localized corrosion and you need to do repairs. They figured this out a lot better because they run inside all the main transmission line. They run the smart pigs that will collect information about the wall thickness. The smart pigs is a very, very specific technology. It's very sophisticated. Each piece of equipment is a multi-million-dollar piece of equipment, but it collects data. Essentially, it gets dragged by the flow in liquid line, by the flow of the oil. So the oil goes 5 miles an hour, and so does your tool, just following along and making measurements all around. So it's a very sophisticated piece of equipment. So they managed to figure out the corrosion. If there's significant mechanical damage, they also pick it up with that tool. And one of the problems in terms of trying to get better at having fewer failures is material deficiencies. They had an improvement, but it's not as much. And the reason is you don't know your steel unless you actually go and test it. And you'll see a lot more why I bring this up in the context of this class. You'll see that in order to learn about how the materials will behave during a tensile test. So one way to do this is to cut out a sample from the pipeline and bring it to the lab, pull on it. You get a tensile strength, you get this stress strain curve. So that's not an option because first there's service, and if you're planning to depressurize a gas pipeline, just taking the pressure out is almost impossible. It's a very, very difficult process. When they have a live leak on gas, they wrap it. So they come and essentially cover the leak temporarily, and then they put a repair patch on it as opposed to shutting down the line. That's how difficult it is, and economically not realistic to do that. So our technology is to go on the outside and test the pipe, and then from analysis infer what the stress strain curve would be if you go to the laboratory with it. Now, the reason I'm bringing this up, and I'll stop going through this, we can continue next lecture, but the steel used to make these pipelines is not the most sophisticated steel. You need so many tons of it that you will use the process that is more economical to make them. So you start with a flat plate and then you bend it. Turns out that the industry standard back then was to bend it cold. And then so the third step here is you put an electroresistance welded seam. So you have your electrodes here, and you just fusion weld it without adding filler metal. And clean up the flash, good for service. What we're going to do as I go through processing is for each of this step, this starting material, if this is not homogeneous, if this is different in the center than on the surface, you could have a variation. When I go and test here, how do I know what the value is in the center? And how do I know what the value is on the inside? And the metal processing, the processing of steel for this type of application that we're going to go through in more details really help to figure this out. It turns out in general you do have an homogeneous microstructure when you start. When you bend it, yes, you work hard on the surface. So you're starting to move on that stress strain curve, so the surface becomes harder than the center. Now, why is this all important? The rule of thumb, the industry standard, still is this tensile test that tells them what is the grade of the pipe, what is the minimum pressure that I can put in this pipe. So ultimately, through our analysis, we want to back determine that, and we want to back determine it for the main reason that not only it's old construction, but they did not have good testing records of what was put into the line. So they'll know, okay, we've put this type of pipe, this diameter, maybe this thickness, and that's it. And they need to know, is it, so the standards for strength, you have a 25,000 PSI yield strength. That's the very minimum. Normally, you're hoping to get at least 42,000 if it's good steel, and you have a 52,000. So these are typical grade or minimum yield strength of the material. And if you don't have a record, maybe you have this quality, but you have to assume this one. So that's a little bit kind of the background of why we're doing this. Now, the way that it works is essentially by scribing the surface. So we have a stylus, it's a cone, and we come apply a constant load. It creates a little groove indication like this. And the technology, what's very special about it is the core device is going to self-align with the surface. That's very useful if you try to go around a pipe. And it creates this groove profile that's very shallow. It's only about 30 micrometer in depth. So it's not destructive at all to the metal. And we collect the information from that profile to back calculate the entire stress strain curve. And we could go through more details of that. The current alternate technology has been to do indentation, and that's possible. We can go over that. You can do a hardness test, but you don't collect as much information, and it's very empirical. And to tell you the truth, they haven't worked this issue. So we're trying to both work, have a better technology, but also have a better ability to back calculate the effect of strain hardening and microstructure gradation. So again, what we're going to go through this semester is metallurgy in hopefully a level that you'll understand. We will talk about grains, we will talk about microstructure, but just in a way that I hope you remember, like what's the difference between aluminum and steel, for example. With steel, the microstructure can look very, very different depending on how it's processed. There are a lot of ways to improve the surface, and joining is so important. You can look into a lot of times we use steel because of the ability to weld it very well and get some good strain of that. And from the feedback from previous students, the welding part is a part that people find interesting and remember, so I'll try to make that a little bigger this semester, and I'll also try to bring in a little bit more failure analysis cases for people who've already been there last fall. So if there's any question, let me know. Again, Professor Eager gave the email address, and I do like to see you guys in class. I understand it's not all the time, but I get live feedback. If something is too complicated, I get to see it firsthand. Thank you.
Okay, thank you. So we meet every day. We will finish up the lectures by mid-October, and then we're going to start doing the presentations towards the end of October. If we do things properly, we'll be done by Thanksgiving. When all your other courses are gearing up towards the end of the term, this one will be done, okay? I was a student here too. I know what it's like. So far as cheating, I'm supposed to say something about cheating. How do you cheat in this course? There's no quizzes, okay? There's no homeworks, okay? This is a course where you get to learn whatever you want to learn. You can do the presentation on whatever you want. Simone and I are available to talk with you about various things. If you want to figure out what modules you want, come see me, okay? So I'll be lecturing tomorrow, and I don't know, are you doing Friday or am I?
I'm happy to do it.
Okay, so he'll be doing Friday, I'll probably be doing Monday. We got to figure out our schedules, but it shouldn't be too much of a problem for you. Okay?